All right, ladies and gentlemen, here is the fourth of the 5 transversal proof videos showing examples of transversal proofs. This particular proof that is on the screen right now is going to be a very important theorem that we're going to be using quite a bit in chapter 4 and on through the rest of the book. This is a proof of what is called the triangle angle sum theorem, which says that any triangle, the 3 angles in the triangle, the 3 interior angles of any triangle must add up to 180 degrees. Notice in the picture that we have triangle BDE. BDE forms a triangle. They have extended one side of DE and they've called that line M. The other point of the triangle, they've used the parallel postulate to establish the only line in the plane that is parallel to line M and contains point B. Name that line, line N. Then they've numbered 5 angles for us, 1, 2, 3, 4, and 5. They tell us that M is parallel to N, and they ask us to prove that angle 1, 2, and 3 add up to 180 degrees. Now it's worth noting that if we do carry out this proof, we will have then proven that that is true for every triangle, every single one, no matter what shape it is, no matter what size it is, this would always be true. That truly is the power of proofs, is once we prove it, it will apply to all triangles. It becomes a rule. So, this does get a little bit tricky in the middle, so please make sure you're paying close attention in steps about 4 and 5. It starts off, though, a pretty standard transversal proof. That is, we start off with the givens. Line M is parallel to line N because that is given. Now, the fact that they're telling us that the lines are parallel should spark us into noticing that we do have several sets of angles in this picture that fit one of our vocabulary words. Angle 2 and angle 4. If we ignore this line, if we don't look at this line, this is a transversal, and 2 and 4 are alternate interior angles. Using the exact same argument, we should notice that angle 3 and angle 5. Again, ignore this line. This is a transversal. 3 and 5 are also alternate interior angles. So the fact that M is parallel to N, what that tells us is that angle 2 is congruent to angle 4 and angle 3 is congruent to angle 5. Because those are alternate interior angles, and the alternate interior angle theorem says that if the lines are parallel, then each pair of alternate interior angles must be congruent. So then we have to tackle the next hurdle. And the next hurdle in this proof is that we don't really have one theorem on the books that allows us to state that 3 angles add up to 180 degrees. I mean, we can look at this picture and notice that when we put angle 4, angle 1, and angle 5 together, that the 3 of them together make a straight line. But that is not an acceptable reason in a proof because it's not a theorem or postulate that we have already proven. Instead, we have to use a very tricky, very clever combination of a postulate and a theorem. So here is that combination. First of all, we need to realize that they've given us letters in this picture for a reason. If we look closely, angle 1 and angle 5 can be combined into an obtuse angle named angle DBC. And the way that we do that is we use a postulate from chapter 2, section 8 that says that we can take any 2 adjacent angles and add them together to form a larger angle. This is called the angle addition postulate. Okay, it was the key term, the key thing that we were supposed to take away from 2.8 was that we can always add adjacent angle measures together to get a bigger angle. So in this case, we could say the measure of angle DBC is equal to the measure of angle 1 plus the measure of angle 5. DBC is this big angle right here, DBC. Notice how that's a combination of angles 1 and 5. Now if we look closely, angle DBC and angle 4 form a linear pair. So we can state that the measure of angle 4 plus the measure of angle DBC must be 180 degrees because the supplement theorem says that all linear pairs, no matter how ugly, always add up to 180 degrees. So using a very simple substitution, we can then generate ourselves an equation where three angles add up to 180. We simply take angle 1 plus angle 5 and substitute it in for the measure of angle DBC. So using a combination of statement 3 and 4 by substituting statement 3 into statement 4, we can generate the equation measure of angle 1 plus the measure of angle 4 plus the measure of angle 5 equals 180 degrees. And I did take a very slight advantage in that I did rearrange it slightly. We plugged 1 and 5 in, and then I moved 1 over to the front, so they'd be in order 1, 4, 5. But really, we are allowed to do that because of the commutative property of addition, which says we can add numbers in any order. So that's just substitution property. Okay. Now, once we have that, that does have three angles being added to 180, but they're not the correct three angles. We need angles 2 and 3 to be in there instead of angles 4 and 5. Well, gee, if only somewhere along the line we had stated that angle 2 was equal to one of those angles and angle 3 was equal to, oh wait, we kind of did. Now, we didn't state they were equal, but we did state that 2 and 4 are congruent and 3 and 5 are congruent. So what we need to do next is turn this line, line 2, from congruent statements into equations. Well, if angle 2 is congruent to angle 4, then the measure of angle 2 must equal the measure of angle 4. If angle 3 is congruent to angle 5, then the measure of angle 3 must equal the measure of angle 5. That is the definition of the word congruence. That's what congruence means for angles. So then we simply have to carry out a double substitution to finish out the problem. I'll show you that substitution momentarily. We are plugging in the measure of angle 2 in the place of the measure of angle 4, so putting this here. And at the same time, we are taking the measure of angle 3 and plugging it in there for the measure of angle 5. So we're carrying out two substitution properties at the same time, which is perfectly legal in a proof. If you have the same reason, you can do two steps at once. So we're substituting in. That finishes the proof. Now again, think about how powerful this proof is. We have just declared that every single triangle, no matter whether it's acute, obtuse, right, scalene, isosceles, equilateral, every single triangle's interior angles always add up to 180 degrees. That's very, very powerful stuff. Okay, so that proof is complete, and we will come back to this theorem next chapter and give it an official name. For now, we're just looking at it as a transversal proof. So one more easy example here, then we'll end this video and go to the final video. Here is another relatively straightforward, simple transversal proof example. Again, there are multiple solutions to this. The idea is that we want to see lots of examples of how to do this so we can start to notice the patterns and develop the process for ourselves. So, like any other proof, we start off with the given. The measure of angle 4 plus the measure of angle 7 is 180 degrees. That is the given. Now notice that angles 4 and 7 do not have a vocabulary basis. They do not have a vocab word that describes their relationship, which means we don't have a theorem, postulate, or converse that we can apply specifically to those two angles. So instead, we need to come up with a third angle that is related to both angle 4 and angle 7. Now we've done a couple of these proofs now, but we haven't done one yet this way. I found overall that the shortest way to get through these proofs, usually the most streamlined way to get there, is to pick an angle that is a vertical angle to either angle 4 or angle 7. So in this case, I'm going to use angle 6. Angle 6 is congruent to angle 7 because they are vertical angles, and the vertical angle theorem tells us that vertical angles must be congruent. So what I can do with that is I can convert it from being a congruent statement into being an equation. The measure of angle 6 equals the measure of angle 7. Because they're congruent. And the definition of that word congruent means that they must have the same measure. So then from there, I'm going to substitute. Again, the only reason I would do that is so that I can substitute, so that I can take the measure of angle 6 and plug it into the original given for the measure of angle 7. So I take measure of angle 6, I plug that in for the measure of angle 7. That generates the equation measure of angle 4 plus the measure of angle 6 equals 180 degrees by the substitution property. Now the reason I'm doing this is because if we look at what angle 4 and angle 6, how they're related, angle 4 and angle 6 are consecutive interior angles. And we have a theorem, actually a converse of a theorem, that says if a pair of consecutive interior angles, like angle 4 and angle 6, are supplementary, that is enough to state that the lines M and N must be parallel. So that allows us to state that M is parallel to N, which would be the converse of the consecutive interior angle theorem. Okay, since those consecutive interior angles add up to 180 degrees, the converse of that theorem states that M must be parallel to N. And if M is parallel to N, that means that all sets of corresponding angles, which would include angle 1 and angle 5, must be congruent by the corresponding angle postulate. All right, so that's 2 more examples down. There are 2 proofs left in the final video. Again, if you have seen enough examples to do your activity, then you don't need to continue. But it's never a bad idea to see more examples before you start doing your work. Thank you very much for your time and attention. 1 video to go.